Good morning, everybody. It's a pleasure to introduce the first speaker of the morning, who is Olena Karpel, who will talk about tail invariant measures on Bratteli diagrams and their generalizations.
Thank you so much. It's wonderful to be here on this conference. Thank you very much to the organizers for making this wonderful event happen. And I would like to talk about joint work with Sergey Bezuglyi, Palle E.T, and Shrey Sanadhya. It is a work in progress. And it concerns generalizations of Bratteli diagrams in Borel dynamics. But I think in order to introduce generalizations, it's nice to introduce standard Bratteli diagrams first. So let me recall what Bratteli diagrams are and why they are very useful for dynamical systems. So a Bratteli diagram is an infinite directed graph which has counted the many vertices and edges. The set of vertices is partitioned into disjoint finite subsets, which we call levels. So there is a 0 level, first, second, third, and so on. And there are finitely many vertices on each level. And the edges are drawn between consecutive levels of vertices. So we can see edges V0 are drawn between V0 and V1, V1 between V1 and V2, and so on. And so edges are also partitioned into finite disjoint subsets. On the upper level, we have just one vertex. And each vertex has an outgoing edge, and each vertex except for the upper one has an incoming edge. And we consider that the edges are directed downwards. And we consider the set of all infinite paths that start at V0, at the upper vertex. And this is our phase space for the dynamical system. And one can introduce topology, which is generated by cylinder sets, by finite paths. So if we fix like shown here in red, any finite path that starts at V0, we can consider all infinite paths that in the beginning pass through this finite path. And so this is a cylinder set, and this cylinder set generates the topology. And with this topology, the path space XB is a compact zero-dimensional metric space, and if there are no isolated points, it is a Cantor set. And so two infinite paths are close if they agree on a large initial segment. And in order to introduce dynamics, one has introduced an order on a Bratteli diagram. First we input a linear order on the set of all edges that end in given vertex. Fix any vertex which is not on the 0 level, and consider all edges that end in this vertex and order them linearly. There are only finitely many of them. This is from the definition of a Bratteli diagram. And then we do it for every vertex. So here is an ordered Bratteli diagram. And then notice that we have infinite paths, which are so-called maximal or minimal. So for instance, an infinite path is maximal if its edge is maximal among those edges to which it is comparable. So for instance, here in red, we have maximal paths. There are only 2 of them on this diagram. If we expand that this diagram is stationary, so it is continuous in the same way to the infinity. And there are 2 minimal paths, which are in blue. So here, for instance, in red, we have each of the edges is maximal among the edges to which it can be compared. And since the space is compact, the sets of maximal and minimal paths are non-empty closed sets. So they always exist for this ordered Bratteli diagram. And then we can introduce the dynamics, the math. So first, we introduced it for the set of all non-maximal paths. So fix, for instance, here in red, there is the beginning of some non-maximal path. Since it's not maximal, it means that there exists an edge which is non-maximal among the ones to which it can be compared. So we take first such edge, like here it is shown in red here, and we take its successor. Since it's not maximal, here in blue is the next edge. Then you see that this next edge has the same endpoint. So we don't change the tail remains unchanged, but now we can have another source point. So here it's the same, but for instance, for 3, the source point is already here. And so to define the beginning of the path, we just connect this source vertex with the V0 by minimal path. And so we obtain an infinite path, which is an image of a given path under the Vershik map. And this way we define a homeomorphism from the set of non-maximal paths to the set of non-minimal paths. And then if this homeomorphism can be extended to a homeomorphism of the whole path space, so it should map all the maximal paths onto all the minimal paths, then we say that we have a Vershik map and the Bratteli-Vershik system. So it's a homeomorphism of the Cantor space, the Cantor dynamical system. And the motivation for these graphs is as follows. So these graphs came not from dynamical systems, but from the theory of operator algebras. And it gave the isomorphism for so-called approximately finite dimensional sister algebras. And just in this graph was the way to encode some embeddings of multimatrix algebras. But it turns out that this graph is very useful also in dynamics. So Bratteli-Vershik came up with the idea of the map, which was later called Vershik map, in measurable dynamics, and he showed that every ergodic automorphism of a standard measure space can be realized as a Vershik map on a Bratteli diagram. And then Herman Putnam and Scow in 1992 refined his construction to use it in topological dynamics, and it will be actually shown also later. They proved that every minimal homeomorphism of a Cantor space can be represented as a Vershik map acting on a path space of a Bratteli diagram, which has unique minimal and unique maximal paths. Okay. Yes, and then Kostya Medinets improved that result and showed that every aperiodic homeomorphism of a Cantor space can be realized as topologically conjugate to a Vershik map acting on a path space of a Bratteli diagram. Then Takashi Shimamura and Tomasz Dobnarowicz and myself extended it to the case of compact invertible zero-dimensional dynamical systems. And Bezuglyi, Kwiatkowski in 2006 proved that in Borel dynamics, every Borel automorphism of a standard Borel space can also be represented as a Vershik map acting on a Bratteli diagram. And these representations are very useful for classification of dynamical systems. For instance, for minimal Cantor dynamical systems, in terms of Bratteli diagrams, one can give a criterion of Kakutani equivalence, also a criterion of strong orbit equivalence. One can define dimension group from a Bratteli diagram. And there are also very good characterizations of some particular classes of Cantor dynamical systems, very convenient. For instance, for substitution dynamical systems, interval exchange transformations, duplex systems. And these Bratteli diagrams are very useful also to describe the simplex of probability invariant measures. Because of the structure of the diagram, one can just study some sequence of matrices and get the information about measures from the look of these matrices. And so there's this theorem which I already mentioned. So the Bratteli diagram is called simple if for any level n, there exists some level below n, so that all the vertices from level n and from this below level are connected by finite paths. And it turns out that any minimal homeomorphism of a Cantor space can be represented as a Vershik map acting on a path space of such a diagram. And this diagram also is ordered and has unique minimal and unique maximum paths. Also, here is the theorem about for compact invertible zero-dimensional systems that they can have a Bratteli-Vershik model such that the Vershik homeomorphism can be prolonged uniquely from the set of non-maximal paths to the set of maximal paths. Yes, sure. Actually, I think I can do like I can keep it. Okay. Sure, no problem. Okay, it makes sense. 1, 2, 3. Thank you so much. Thank you. So it's okay, right? Okay. Yeah, so one can for a case of compact invertible zero-dimensional system, if the set of its aperiodic points is dense or the closure of this set misses just one periodic orbit, then we can also represent such a system as a Bratteli-Vershik model, such that the Vershik map prolongs to the set of maximal paths in a unique way. So these are kind of theorems that you can obtain. And there is also a notion of tail equivalence relation. So two infinite paths are called tail equivalent if they coincide starting from some level. So for instance, in red and in green, they're at the beginning of these paths, then they come to the same vertex, and then their tail is the same. One can define invariant measure with respect to this tail equivalence relation. So the measure is called invariant if for any two cylinder sets such that corresponding finite paths end in the same vertex, their measures are the same. So here we have in red the finite path that generates one cylinder set, in green another cylinder set, and for invariant measure, the measures of these two cylinder sets should be the same. And then we can consider ergodic measures with respect of this tail equivalence relation. And it turns out that the measures for a periodic tail equivalence relation, the measures which are probability measures which are invariant with respect to this equivalence relation are the same that are invariant with respect to Vershik map. That's because they have like basically the same orbits, the tail equivalence relation and the Vershik map, except for many maximal and minimal paths. But for a periodic equivalence relation, they are wandering, and so their measure is 0, and we get the same sets of invariant measures. And so we can forget about the order and consider just the equivalence relation to study invariant measures. And also it is a bit more general situation, and continuous Vershik map does not always exist for any Bratteli diagram, but equivalence relation always exists. So we can always consider this equivalence relation. And then the whole Bratteli diagram is completely given by the sequence of incidence matrices, which show how edges are drawn between consecutive levels of vertices. So for instance, here, well, it's historically defined that we should first look, for instance, to define F0, we look at a vertex on the first level and then see how many edges are going to their upper level V0. So here we have 1 and 1, and we write it in the rows. Then for the second matrix, we have 1, 1, and 1, 2. So there is second incidence matrix, the third one, 1, 1, 1, 3, and 1, 1. And so on. And so all the information about simplex of invariant measures should come from this sequence of matrices. And so, why these diagrams are really very convenient to study invariant measures, it's because of the structure of the diagram. So if mu is any Borel non-atomic probability invariant measure, denote it's invariant, so the measure of cylinder set just depends on the length of this set and on the terminal vertex. And the measures of all such cylinder sets which have the same terminal vertex are the same by invariance. And so we denote by PWN the measure of any such cylinder sets which ends in vertex W on level N. We can see that this cylinder set is partitioned into cylinder sets of which are one path longer, one edge longer, right? So, and incidence matrix tells us exactly how these edges are drawn. Yeah, yeah, it's okay. Yeah, so we can say we can see that this measure of a cylinder set that ends in W. One. Okay, great. Yeah, no. So I can continue, right? Thank you so much. So we have that this cylinder set is partitioned into the longer cylinder sets, and so the measure of this cylinder set is the sum of the measures of these longer cylinder sets, and the number of these cylinder sets is given by the elements of incidence matrix. So we get this beautiful formula, which we can write down in a vector form. And we can see that Pn is the vector of the values of measure on cylinder sets. And then if Pn is a vector of the measure of cylinder sets on level n, and Pn plus 1 on level n plus 1, then these vectors should be connected with the help of incidence matrix on nth level with this formula. Right? Yeah. And so it holds for any Bratteli diagram. So suppose that we have Bratteli diagram B with incidence matrices Fn, and the tail equivalence relation is aperiodic. Then on the one hand, if we are given a probability invariant measure and Pn is its sequence of values on cylinder sets of lengths n, then this formula should hold. And on the other hand, if we have a sequence of vectors which are non-negative and which are connected with each other with the help of incidence matrix, like this, so we get like an inverse limit, then this sequence of vectors generate invariant measure. And so we can like study like the number of invariant measures, of ergodic invariant measures. We can look at the number of at the extreme points in this inverse limit, and how many. So for instance, if there is only unique sequence of vectors which satisfy these conditions and which are non-negative, then we get unique ergodicity. There is only one invariant measure. And in case of stationary Bratteli diagrams, this sequence of vectors is given by Perron eigenvector. So a diagram is called stationary if the incidence matrix is the same on all levels. We just draw the diagram in the same way. And then by Perron, so we have some non-negative matrices, and by Perron-Frobenius theorem, there are Perron-Frobenius non-negative Perron-Frobenius eigenvectors and positive Perron eigenvalue, which is greater than 1. So we have this formula. A is the matrix transposed to incidence matrix. Just for convenience, X is a column vector. And we can define the measures on cylinder sets by the following formula. We just take the coordinate of this eigenvector, and this coordinate, actually, there is I is the same as W, sorry. Like here will be let's maybe go to example at once. So here we have a Bratteli diagram which is stationary. It's drawn in the same way, and it has the following incidence matrix. We have here 1H, 1H, 1, 2, 1, 1, 0, 1, 2, 0, and 0, 1, 3. And it's reducible matrix. It has two eigenvalues, and both of them generate two Perron eigenvalues, distinguished Perron eigenvalues, and both of them generate Perron eigenvector. With these eigenvectors have no negative coordinates, and they give us two different probability ergodic measures. So for instance, consider this second one. We have lambda equal to 3, and these are coordinates of the eigenvector. So here we have the first vertex. So we take the first coordinate of the eigenvector, and the length is just 1. So we divide by lambda to the power 1 minus 1. So we don't divide by lambda at all. So we have here 1 over 4, here 1 over 2, here 1 over 4. Then we go, if we take cylinder sets which are longer, we here divide by lambda to the first power. So we take this as the first vertex. Again, we have the first coordinate and divide by lambda to the power 1. This is so the measure is invariant. This cylinder set has the same measure. It's again the first coordinate and the same length. And if we have a cylinder set that ends in the second coordinate, we take the second element of coordinate of the eigenvector and again divide by 3, and so on. Here we divide by 3 squared. Okay, and so this is the way and the number. So all ergodic invariant measures come from this non-negative Perron-Frobenius eigenvectors. So this is a complete description of ergodic invariant measures for stationary Bratteli diagrams. And there is also a description for finite rank Bratteli diagrams, which are the diagrams which have uniformly bounded number of vertices on each level. So here is the uniform bound D, and it turns out that all the measures can be obtained from some subdiagrams. So for instance, here, we can see that this reducible matrix has block form, And this here, this block corresponds to this red subdiagram, and this block corresponds to this green one. And in fact, we can obtain these two measures as extensions from subdiagrams. So for instance, this second measure that I described before, it can be defined just on this odometer, just on this green subdiagram. We can define a measure and then extend it to the whole diagram by with the help of tail equivalence relation. So we know that we want to get invariant measure. So the measure of this cylinder set should be the same as the measure of already defined cylinder sets. And with the help of equivalence relation, we can extend the measure to the whole diagram, and we will get exactly the same measures here. And so it is true for all finite rank Bratteli diagrams. It turns out that all ergodic invariant measures actually sit on some subdiagrams and can be extended from these subdiagrams to the whole diagram. And here is also an example of the theorems that one can get, which describe how many ergodic invariant measures there are. So we basically find how many there are these subdiagrams which are uniquely ergodic and which can support a finite ergodic measure for the whole diagram. So for instance, if we have a diagram with just two vertices on each level, which has incidence matrix which equal row sum properties, so an plus cn is the same as dn plus bn, then there are two ergodic invariant measures if and only if the following condition holds. So it means that actually this measure extension is finite, and there is a unique invariant measure if and only if this condition holds. So this is an example of the theorems which Bratteli diagrams can give us. And also Bratteli diagrams can give us examples, can provide us with examples of homeomorphisms. So for instance, if you want to build a minimal homeomorphism, which has zero entropy and countably many, infinitely many probability ergodic invariant measures, then we also can build it using our knowledge of Bratteli diagrams and subdiagrams. So for instance, here, odometer is a Bratteli diagram which has unique vertex on each level. So here we have countably many subdiagrams which are odometers, and each we can put a measure on each of these odometer, and under these conditions, the extension of these measures give us finite ergodic invariant measures on the whole diagram, and there are no other measures. So that gives us zero entropy, homeomorphism, which is one can put left to right order, then it will be zero entropy. It has countably many finite ergodic invariant measures, and it's minimal. And now we decided to see how much we can generalize these results for the case of Borel dynamics. So we consider a pair xt, where x is a standard Borel space and t is a Borel automorphism, and we define generalized Bratteli diagrams, which are infinite directed graphs. The only difference is that the vertex set now is countable, like the levels are infinite countable. Here, and we also a little bit changed the indices. So we start with V0 is not unique one vertex, but it also consists of countably many vertices. And then we have V1, V2, and so on. And also the edges are drawn between only consecutive levels of the diagram. And we have an additional condition. We want that we ask that every vertex has only finitely many incoming edges. So in terms of corresponding Kakutani-Rokhlin partitions, it means that every tower has finite height. And so we can use telescoping and so on. So this is a generalized Bratteli diagram, and Bezuglyi, Dooley, and Kwiatkowski proved that every aperiodic Borel automorphism of a standard Borel space is isomorphic to the Vershik map acting on the path space of an ordered generalized Bratteli diagram. And this diagram is such that it has no minimal and no maximal paths in that area. And there exists, so if we focus on stationary diagrams, there exists Perron-Frobenius theory for infinite matrices, which we can also use to define invariant measures. So here we use the book by Kitchens as a source for these theorems. So a non-negative infinite matrix is a standard definition for finite and infinite matrix, the definition of irreducibility. Then there is also definition of aperiodicity, the same as for finite matrices. And it's turned out that if we have a real non-negative, irreducible, and aperiodic infinite matrix, then the Perron eigenvalue is defined like this. And it already can be finite or infinite. And the matrix is called recurrent if the following sum is infinite, and it's called transient if it's finite, and this terminology comes from Markov chains. There is a generalized Perron-Frobenius theorem, which tells us that for any real non-negative, irreducible, aperiodic, recurrent, infinite matrix, we can define this lambda Perron eigenvalue and suppose it's finite. Then there exists strictly positive left and right eigenvectors for the matrix A, and they are unique up to constant multiples. And also we can define a positive recurrent matrix as the one such that this scalar product, not scalar, but this product, this will be a number which is finite. And if A is positive recurrent and this product equals to 1, then the product in reverse order is the limit of the following fraction, an over lambda n. And we can use this theorem to prove that if we start with some ordered stationary generalized Bratteli diagram, which has the incidence matrix, which is irreducible, aperiodic, and positive recurrent. So we have this equality. And also we assume that the corresponding eigenvector, which will generate the measure on the diagram, has the property that the sum of its coordinates is equal to 1. And actually, we couldn't find in the literature what are the conditions. If someone knows, it would be really helpful. What are the conditions on the matrix so that it has an Perron eigenvector for which the sum of coordinates is finite. Because if the sum is infinite, it will give us a sigma finite infinite invariant measure on the diagram. And so we prove that under these conditions, there is a unique probability invariant measure for a Vershik-Borel automorphism, which is positive on cylinder sets. And so that's how we can actually define this measure. So in the same way as for usual Bratteli diagrams. So we start with a cylinder set, and we have our eigenvector, we have eigenvalue, and again we look at the vertex at which the cylinder set ends, and at the length of the cylinder set, and we get the formula for the measure of a cylinder set. And then we use ergodic theorem to prove that there is no other ergodic probability invariant measure which has takes positive values on cylinder sets. So suppose there is another one, and denote by PWN its values on cylinder sets of lengths n, which end in the vertex W. Then by Birkhoff-ergodic theorem, we can show that each such number is the following limit, where EWV is the number of finite paths between W and V, and H of Vn is the number of all finite paths that end in V and start in zero level. So here we can see that the number of paths between V and W is the number of times, if the number of times that the Vershik map hits. So we use the Birkhoff-ergodic theorem for characteristic function of a cylinder set, and so the measure of a cylinder set is equals we can consider the number of times we enter the cylinder set and divide by the number of all here of the whole height of the tower. Right, so we use a subsequence in the Birkhoff-ergodic theorem, and this subsequence is the number of these finite paths in the tower. And so we have this formula, and then we have used the Perron-Frobenius theorem, like that one that was here, this one, and we can show how this EVW can be defined with the help of determined with the help of incidence matrix. So this number of finite paths between V and W is exactly AVW, and to the power n, big N minus small n. So this will be this number, and number in their denominator will be the number of the all heights of the tower. And so we use that Perron-Frobenius theorem and get that any other probability ergodic invariant measure should have this, which takes positive values on cylinder sets, should have the same values on cylinder sets as that measure that we are given here in the beginning. And here is an example of such a matrix. which has a finite, so here we consider A is a transpose to the incidence matrix, and this eigenvector, it should be actually a column vector. So this, it has no, it is positive, and it's the sum of coordinates is finite. And here lambda is equal A plus 2B, and this matrix has an equal column sum property. So we can get this eigenvector, and it determines the measure on the diagram. And such diagrams are example of Bratteli diagrams of bounded size. So we think it's something, a generalization of Bratteli diagrams in Cantor dynamics, which is, so it is in Borel dynamics, which is very close to Cantor dynamics. So it's maybe, it's like generalization, which is the most close to the finite case. So a generalized Bratteli diagram with incidence matrices if Fn is called of bounded size, if there exists, as is for every n, there exists a sequence of natural numbers Tn, Ln, such that, let's look at the picture. For instance, we fix level n+1 and take any vertex v from there. Then Ln is the bound on the number of edges incoming to v. So, and it is uniform for all the vertices on this level n+1, and the sources of the incoming edges also belong to some interval. So, since we have generalized Bratteli diagrams, we can enumerate all the vertices on each level with integer numbers. So we can we can look at v as some integer, and we can see that the sources lie in the interval v minus tn, v plus tn. So it could be tn minus, so tn's is not necessarily the same number, but for simplicity, we just write tn instead of tn minus and tn plus. It will not change our considerations. It will just, to simplify the notation. And we also assume that there is an edge between v minus tn and v plus tn and v, so that the diagram is irreducible. So the corresponding incidence matrix is irreducible. It is basically, it will also have this form, which is called banded matrix. So a matrix is called banded if it's all non-zero entries belong to a band along the main diagonal. So for instance, like it was on this picture in red, so the red elements are the only non-zero elements, and here they all belong to the band of width 3 along the main diagonal. And if we have a Bratteli diagram of bounded size, then all its matrices, matrices are banded, and the width of the band is 2tn plus 1. And for such matrices, the cylinder sets are compact. So we are in a generalized situation. So of course, our phase space is not compact, and our cylinder sets also need not to be compact. But for these diagrams, they are. So we have a locally compact phase space, and it follows actually from the definition of this Bratteli diagram of bounded size. So fix any vertex W on level n. By definition, all the incoming edges belong to this interval from W minus Tn minus 1 to W plus Tn minus 1. And then by induction, we can show that on 0 level, we also have the bounded interval to which the sources of the finite paths that end in W belong. And also we can go downwards. And again, from the boundedness, it follows that the vertices that can have access to W only have, can lie in this interval. And also we can go downwards. And for each level n plus m, we also have the intervals where can lie the ranges of finite paths that start from W. And so we get these subdiagrams, which we call cones, which are assigned to any vertex W on any level n. And then we also get so-called slanting sets. So if we start with a level W, and I wanted to say that from this picture, we can see that this space is locally compact, because if we have any cylinder set that ends in W, you can see that then all the paths that lie in this cylinder set actually belong to some finite Bratteli, like usual Bratteli diagram. So it gives us a compact space, a compact set. And so the slanting sets, we start with a vertex W on level V0, and then we go to the rightmost edge through the right. So like here, we pick
the edge which lies to the right, and then again the edge which lies to the right. So basically we took this like this, take this boundary here, and we can consider the infinite paths that such that their vertices all lie to the right of this slanting path. And so such sets are, so this way we define ZW plus, and in the same way we can define ZW minus if we go through the leftmost edges. And these slanting sets are tail invariant, closed, nowhere dense sets with respect to the topology generated by cylinder sets. So it follows, so the closedness is really trivial. Then if we take, for instance, why they are nowhere dense. If we take any cylinder set which generated by finite path, which lies inside this slanting set, then we have this cone structure. So this cylinder set eventually will go out from this slanting set. So it will always have a cylinder subset which does not lie in this slanting set. And also this cone structure shows us that these sets are invariant with respect to tail equivalence relation, because also we take any path from here and all its tail invariant, like all the infinite paths which are tail equivalent to this path will lie in these cones, upper cones. And since we took this slanted set, the whole upper cone will also lie only in this slanted set. So we get this R invariance. And also we have a result about this, about stationary Bratteli diagrams, which have, so suppose we have a generalized stationary Bratteli diagram with an irreducible aperiodic incidence matrix, and we prove that the tail equivalence relation is topologically transitive. And if F is banded, then this relation is not minimal. So the fact that it is not minimal follows actually from this observation that we have an invariant closed subsets. So we cannot have minimality, but it turns out that we have topological transitivity. And the idea of the proof is to show that such a diagram has vertical paths, which such that their orbits are dense. Their orbit, like their equivalence classes are dense. We use also results from the book by Kitchens. If we start with any vertex I on 0 level, it turns out that for this irreducible matrices, this is irreducible incidence matrix, we have the result that there is number n, natural number n, such that for all k greater or equal than n, f to the power k ii coordinate is positive. So that means that, for instance, we start with this vertex I on level 0. Then there is a path of length n to the vertex I on level n. And then there is a path of length n plus 1 to the vertex I on the level corresponding level v2 n plus 1, and so on. And we can do like this. And we show that, so we obtain the path, infinite path, which we draw in blue. And then we show that it's in its tail equivalence class, there are paths which will visit any given cylinder set. So if in red there is some cylinder set which ends in vertex J, then we can again use the same procedure and write down the infinite path which passes through J, and on level M, then M plus 1, and so on. And then we use the irreducibility. So for any I and j, there is a number L such that f to the power Lij is positive. So, and since we took here all possible natural numbers greater than n, and so we picked here, and here, yes, right here, n plus 1, n plus 2, we can, and here n plus m, n plus m plus m plus 1, n plus m plus m plus 1 plus m plus 2, we can get all possible remainders under division by L. So we can always find two vertices such that here 3n plus 2 minus n plus 2m plus 1 will be divisible by L. So there will be a path between these two vertices. And so in this way, we show that there is an infinite path in this tail equivalence class of this path that visits this cylinder set. And I think I will stop here. Thank you very much for your attention, and very happy birthday to Felix. Thank you.
Are there any questions or any comments?
Oh, there are very many, like we have just started. So for instance, we don't know if the only measure comes, so we know that this Perron-Frobenius eigenvector gives us some measure, but if we don't know if it's unique invariant ergodic measure, if it's the same as for usual Cantor dynamics, maybe there is another measure that comes from somewhere else. And we don't know again these conditions. So there are also matrices such that lambda is infinite. So for instance, it can be banded matrix if here we have on the diagonal like elements n to the power model n. So they grow really fast. And then in this formula here, so we have here n to the power n, and this limit is infinite, and we don't know, maybe we have a hypothesis that there is no probability, so there is no, of course, this Perron eigenvalue, no eigenvector, and maybe there is no probability ergodic invariant measure. So there exists Borel automorphisms which don't have these measures. And since by theory and by Bezuglyi, Dooley, and Kwiatkowski, any homeomorphism can be realized on a Bratteli diagram. So there are Bratteli diagrams which do not have this probability ergodic invariant measures, and maybe that is an example of such diagram. And we have actually tried to generalize all the results we know in Cantor dynamics. We haven't looked at this question of orders, is it true that every Bratteli diagram can be ordered so that it has like no maximal and no minimal paths, for instance, or like when we get Vershik homeomorphism on the whole path space, when can it be so there are like many questions. So thank you very much.
Are there any more questions from the audience?
Is there a characterization for the Bratteli diagrams that have finitely many ergodic invariant measures? Because
so you mean for in Cantor dynamics or in?
Yeah, maybe even for the first, not the generalized.
So we have, for instance, I mean, I put some slides back here. So there is a criterion of, for instance, of unique ergodicity, which can be, which basically means, yes, so in terms of incidence matrices, yes, we have the criterions when there we have, so finite rank Bratteli diagrams, for instance, always have only finitely many probability ergodic invariant measures. For infinite rank, we have sufficient conditions. So we basically we should have only finitely many rich subdiagrams, which have many edges, which are uniquely ergodic. We can put measure on there and then extend to the whole diagram, and there are no other ergodic invariant measures. So we have conditions on the sequence of incidence matrices. They should have some blocks where the which have majority like the rich elements, big elements, and in the row the other elements should be really small, and then the extension of the measure will be finite. Yeah, so we have, but we have just sufficient condition, because I think it's like we think that on Pascal diagram, that Pascal diagram that it doesn't have this, we cannot see at once all the subdiagrams. So there is a question, does every ergodic invariant measure come from a subdiagram? And we think that in Pascal diagram, maybe no, there are this uncountably many ergodic invariant probability measures, but well, we have some sufficient conditions when they do come from subdiagrams, and then we can count their number by the number of the subdiagrams.
I see. Thank you.
Thank you so much.
Are there any more questions from the audience? Are there any virtual questions? If not, perhaps we could thank the speaker again.
Thank you very much.